It's just like, it's the thought that counts.
All right. Gauss's law continued. Here we go. So what this is talking about is this end and that end. I'll draw a front view. Have a conversation. Tell them why you think so. Correct answer is A, 0. Okay. There is no flux going through here. It's like looking at the cross-sectional area of this, like this. Does that make sense? Like the electric field is going this way. None of it passes through here. Sorry. Okay. Good with that? So no flux. Which is nice. Like that's pretty definitive. Okay. What about through the wall of the cylinder? So same scenario, but through the wall of the cylinder. Think in your brain. Thumbs up when you have a guess. Converse.
You need the no, I think this come on times of the building. Oh, yeah, yeah, okay, yeah, true. So it's not changing like, I think it's time to like. So. Yeah. Well, I bet area surplus.
Okay, correct answer is B, bountiful buffaloes. Okay, so we are looking at, notice how the electric field intersects with this at a right angle. So it's, you don't have to do any angles. It's just all of it's perpendicular. Okay, that's what we're going for. That'd be great. If we can do an all or nothing without angles, life got way simpler. Okay, So on the edges, it's nothing, and on the wall, it's the length of this. So we like perforate this, lay it out into a rectangle. Length times the width is the circumference. So that would be the area times, oops, not magnetic field, sorry, electric field. Would be equal to your flux. Good? Toby. Beautiful question. So if it's an infinite line of charge, the charge that was, so let's look at this point here. This charge emits a field there, but the field that this one equidistant, and so the x components cancel out, and you just get the y components adding up. Good with that? So if this was a finite rod, then you'd have to go hardcore calculus to figure that out. Okay, so so this is a classic problem for free response. What's the electric field created by a line of charge that has a linear density of lambda at a distance r away? Okay, so we're starting with Gauss's law. We draw a Gaussian surface that looks like a cylinder. You know, like in chess, how you have like certain stock moves. You get some stock moves for Gauss, like, oh, it's an infinite line of charge. I need to draw a cylinder, and here we go. Okay. So your so we established this. The electric field's the same at all places, so I can like pull that out. And then we established that the area was 2 pi r times the length. Good with that? Now we need to figure out an expression for the charge enclosed. So, bless you, we incorporate our ratio of charge per unit length. Because we can't figure out, the line is infinitely long, like there's, and if it's infinitely long, it's going to have an infinite amount of charge, like what? But we just look at this ratio. And we're going to express this certain amount of length has that amount of charge for that amount of length. So we can express that as lambda times L over epsilon naught. Does that make sense? And our lengths cancel. So we get 1 over 2 pi epsilon naught lambda over r is equal to your electric field. Good with that? Some people are like, that's so close to 4 pi epsilon naught. Like, why don't we just... And so some people really like doing this. Lambda over 4 pi epsilon naught. Personally, I'm like, let's just, but whatever. Okay? You see how we did that? Josiah.
Sorry.
it's equal to K. So I could express it like 2K lambda, 2K lambda over R. Do not memorize that ending point. Understand where it comes from. And while you're doing this, I want you to check out. You've actually done this before. And that was when we did that there with calculus. And I said, yeah, they do some magical math here to like factor out to get the stuff. And then we make L is equal to infinity. And when we do that, what we get is that expression there. Cool with that? Gauss's law. Way easier than that. Don't do it that way. That is absolutely ridiculous. I don't even know how they got there. I mean, I do once I've seen the solution, but like for me to like recreate that, I'm like, ugh. They do some funky factoring. The black stuff? No. You will have to do the green stuff. Absolutely do the green stuff. Okay? Good with that? So that is a line of charge. Questions there before we move on. Okay, a plane of charge. So granted, this is fabricated just like an infinite line of charge is fabricated. This is a two-dimensional sheet with zero thickness that is has a uniformly surface charge. Okay, so I'm going to draw my Gaussian surface like this. So this is another stock shape that we find. Okay, so remember that when you have a plane of charge that's infinitely wide, the electric field is constant regardless of how far away you are. Right with that? Remember that? Factoid. Okay. Have a conversation. Correct answer is? Correct answer is C. Because there's two areas. Along the wall is how much flux? 0. Just on the ends. Okay? And you have two of them. Both are going out because it's positive going outward. How are we doing with that claim? Okay. So, employing Gauss's law, we're just going to leave this. Well, I'll come back to this. You come up with the expression for Qn inside the Gaussian surface. Keep it real simple in terms of A. What would be the charge enclosed? Sigma is equal to charge enclosed over A. So it is just sigma times A is equal to charge enclosed. Okay, so now you put together this, what we just talked about, this slide and the previous slide for Gauss's law. We talked about the flux on the first side. We talked about the charge enclosed on this slide. Okay. How do we do? Not too bad, yeah? Okay, I'm going to leave it as area because on the AP test, sometimes they give you a Gaussian surface that looks like this. I've seen other questions where they give you a Gaussian surface that looks like a block, rectangle. Does that make sense? And it's just the area. Like they just say A for area. If they get specific, like give you a radius, well, you can figure that out. Or a length of side if they want to specify, but the areas are going to cancel out. Good with that? Okay, so that is the electric field due to a plane of charge that's uniformly distributed.
So if the areas are going to cancel out anyways, why would they want us to specify?
Could help me out with that question.
So like, does it essentially not matter what shape it is?
It does not, so long as this side and that side are identical. Because you don't, yeah.
Okay. Yeah,
Does that make sense? Yeah, and you need to because you have two of them. Okay. Good with that? That is Exhibit B. Exhibit A was this. Exhibit B What is this? Exhibit C is a charged conductor. Okay, and okay, stop writing and just listen. Stop writing and listen. On a Gaussian surface for a conductor, you will always make one of the ends in the interior of the conductor. A Gaussian surface for a conductor, one of the ends will always be on the interior part of the conductor. Okay, now you can write stuff. See if you can set up Gauss's law. So it has a certain surface charge density. Okay. See if you can set this up with the fact that one of the ends of the Gaussian surface is on the interior part of the conductor. And just leave it in terms of A. So we're looking for electric field. We're going to say we have a flux, an area of A. There's no flux here. There's no electric field on the inside of the conductor. That is the important part. That is why we stuck one of the ends, bless you, on the interior part of the conductor, because there is no electric field. So there's just one of them, versus a plane of charge had one on either side. But in the interior of a metal, there is no electric field, so there's no flux here. It's just going this way. Okay? See the difference there? And here, the charge on the enclosed is just your surface charge density times your area over epsilon naught. It's your electric field for a conductor. That, folks, you need to know where this comes from, but that would be worth memorizing. That little equation, that conclusion to this comes up a lot. And it would be beneficial if you just had that knowledge in your back pocket of like, well, I know this is true. This will always be the case. Now, that surface charge density could change as you go around here. So we're going to make this small. But at this location, this infinitesimal Gaussian surface, that is true. So,
how do you know that the walls of the cylinder have flux of zero?
Great question. So the question was, how do you know that the walls of the cylinder have a flux of zero? We're going to draw this small enough that our electric field This is a rule we have not established yet, but the electric field will always be perpendicular to the surface of the conductor. So if we draw the surface small enough, it'll be perpendicular, so parallel to the walls of the Gaussian surface. You all right with that? Great question. Okay. Good with that. Other questions? Okay, those are your basic shapes. We talked about a charged sphere yesterday. It's Gauss's law. It's just point charge. Infinite line of charge, infinite plane of charge, and a conductor. Those are your basic shapes. Okay, we can do a lot with those 4 things. Josiah.
So according to that formula, is the electric field constant no matter the distance away you are?
Great question. So this is just at the surface of the conductor. Great question. For an infinite plane of charge, yes, it does not matter how far you are away from. For a slab of metal, it absolutely does. But that's just at the surface of the conductor. James.
What happens when you stop assuming that the Gaussian surface is infinitesimally small?
If we stop, then we have to do stupid stuff like there's flux coming out of the sides, and we have to do some crazy math. This is not an approximation. This is like we know it because we've used calculus to make this infinitesimal. Like that's not we're not approximating. We're just making this test sample really small, if that makes sense. And then we add that all up. Tell me. Yeah. Yep. Yeah, it does not matter. Like, yes, it would matter how long that is. To evaluate, to get to this, it's short, it's small, like it's right at the surface. Right at this point, we can use that to evaluate that. Good with that? Now, this will change at different parts, and we'll talk about that later. But at a certain point, you can tell, you know how strong that field is. Good? Okay. We're going to start applying those 4 basic shapes. Okay? If you see this, I apologize. One textbook used nu instead of sigma. I'm like, ah. All right, here we go. So, we have a negative plate charge Q, like overall. So, figure out the Gaussian surface or the electric field. Figure all this out for one side. I'll give you a hint that you need to consider. Just consider that the charge is, where's my mouse? The charge is distributed on this side and this side. All of the charge is distributed on this side and this side. I'm not really worried about that part, just the 2 sides. Talk to your neighbor.
Yeah. Well,
Calculate.
It's negative Q overall. The whole shape has a charge of negative Q.
-2/2. Okay. So you would, for the left side, you would do that with the thing to the left side, which would be over 2 and whatnot. Then you would have to add that to 1.
yeah, it's just nice.
That doesn't seem right. Is that the right key? Corridor area. Twice that. Mathematically, I see it, but conceptually, I'm not seeing it. I feel like the 2 should be down below. Charge over half the charge. Did I do some math wrong? I feel like. I agree with this. All right, well, we're just going to proceed on. That is not, doesn't sit well with me. Ugh. I'm going to chew on that first. I feel like my gut says.
Should it be negative?
I don't really care about the negative or positive. Yes, it technically. I'm just looking. I'm concerned about the magnitude. Yes, it would be negative flux. Yo, what's going on, man? I'm not going to let you in my head because. All right, so starting a story. Dogs, come on, man. What is going on here? All right. I'm going to start a story here. Okay, so we got a metal plate that the charge is distributed on both sides. Why would that be? Okay. All right, here's the story. We have another plate of charge that has a charge of plus Q. It's a metal slab. Okay. What happens to the charges in the plate as I bring this positive plate near this negative plate? What do you think will happen? They're plates, it's like the pi 10 compared to an electron. When the electrophorus, it's really thick. Like this is not a plane of charge, this is a plate of charge. Everybody have a guess what happens? So we bring this close. Here's what goes on. Polarizes. Okay? Technically, like this side is more accurate. The electrons move close. And here, the protons don't move. The electrons move to the far side. Good with that? Okay. What we've essentially made is a capacitor. You right with that? Okay. So, what happened to the surface charge density? Right, this over here. Electric field. 2 times surface charge density. Oh, man, that's not so long. Thought I had it, and I didn't. It left me. Dogs. Such a irking thing. All right. So what happens to the surface charge density? Increase, decrease on the inside of the plate. Increase or decrease? Increased. Everybody good with that? Okay. So, what value? So the values. Yeah. So it increased, and now it is all the charge over the area. Should have a. Does that make sense? The surface charge density, because these things polarize, you now have a higher concentration of charge per area. Good with that? Okay. So here's what I'm trying to show you. When we were doing when we were doing this slide. We looked at the electric field from each of these. This contributed one, this contributed one, and we added those together. Okay. Here's a really important subtle detail. When we do the Gaussian surface, the electric field that we are describing is not the electric field just by one plate, but it is the net electric field. That is super crazy important to recognize. It's by all the charges. Sorry, it's the electric field contributed by everything, even though the charge included in the Gaussian surface doesn't contain that. Okay, so these guys over here are contributing to the electric field like we talked about here. Like, oh, look, this one has an electric field. Oh, that one has an electric field, so the net electric field is this one. Okay. When we use Gauss's law, it does not calculate. Catch this. This is a pitfall a lot of people fall into. It does not calculate this. It calculates this. It's everything. It's a powerful tool. How did that happen? Because of that polarization, because of this. Because of this motion there. This charge density doubled because of the presence of that. That's why we can conceptually grab a hold of just these charges and draw a Gaussian surface just like this to find the net electric field, and that's accurate. You don't have to do it on both sides. It can be one side because the charge enclosed has been influenced by this over here. Does that make sense what I'm trying to get at? So this is something I struggled with when I was digesting this. I'm like, wait, how does that? It's because things, it's not just one plate, it's all of this, the net, it's the total. Good with that? Okay. So we can find let's see. Okay, so if we looked at the Gaussian surface here, assuming that all the charge, in an ideal sense, all the charge is over on this side here, there's no charge enclosed. So the electric field out here is 0. Here the charge enclosed is this. Here the charge enclosed is this. You're going to get the same results, identical for the net electric field. You don't have to do both of them. It's just one or the other. And then out here it's 0. Right with that? So nu is sigma. So surface charge density. tell your neighbor. Correct answer is F. Fantastic fish. Flopping fish. Okay. This is the surface charge density on a conductor. Okay. That surface charge density is the charge on that. Out here it's 0 and 0. All right with that? Last slide for the day. Have a conversation.
Oh, okay, that's actually, it's tight.
Direction matters.
I'm going with
Number 5.
I love how you use, I gave you a very simple.
Correct answer is electric eels.
I couldn't do it.
Yeah?
I could.
Get at that? So we're assuming that all the charge goes on the left side of the plate and the right side of the plate. Inside on the right side of the plate on the interior, there's nothing, no charge. Here, left side of the plate, no charge. Good with that? Okay.